Okay. Okay, so because this is the first day of the week, I'm going to try to give you an overview of, radicals and the definitions so that you're not just like going into this completely blind. And then we'll do the product and quotient properties of radicals. So we're going to start with the definition of a square root because most people, square root is something you've seen. We've worked with it when we're doing order of operations. So b, just some number b, is a square root of a if b squared equals a. So if you square a number like, let me get my pen out if I can get it working. So like 2 squared equals 4. So 2 is a square root of 4. And so we would have like the square root of 4 gives us 2. But there's also a negative version because when you square a negative, you also get a positive. So I've got an example of 3 and -3. You square those, you both get 9. So the square root of 9 is both 3 and -3. There's 2 possible square roots. And that symbol is called the radical sign. So usually we'll just call it the square root symbol, but it's officially known as a radical. So most of the time we want the positive value out of the 2 square roots. So that's called the principal square root. And we always use the positive when we're not solving. So what we're doing today is not solving. So we're going to assume we just want the positive answer. If you're solving, meaning you have an equation, you have an equal sign, then you need to have both the positive and the negative. But we are only doing the positive today. And when you're using a calculator, like if you put the square root in the calculator, it always only gives you the positive. So you have to be aware when you need the positive, when you need both, because the calculator will not give you both. So we have square roots. We also have what are called nth roots, where n just stands for another number. So our square root is basically undoing an exponent of 2. So the nth root is undoing an exponent of n. So the number, the n, that value is basically, that's telling you what exponent you're undoing. And then that's also the name of the root. So we use the same symbol, but we put an n above the little v thing there. And since it's above, it's actually a superscript. And so that number that's up there, that n, is called the index. And then what's underneath the symbol is called the radicand. So this is how I usually write it. I make sure that it's very close to my symbol so I don't confuse it with an exponent. So that's a cubed root, as if it has a 3 up there, and that undoes, I'm not sure the proper how you but that undoes an exponent of 3. And you've got a 4th root, which undoes an exponent of 4, and you can have any type of root. You can have 100 there if you want. So for square root, we usually don't write the number, but you can also write it with the number 2 to indicate a square root. And I've mentioned that the one with the 3 is called a cubed root, so that undoes or reverses exponents of 3. So the cubed root of 8 gives you 2, because 2 to the 3rd power is 8. And the cubed root of -8 gives you a -2, because -2 cubed is -8. So we are going to be doing a lot of stuff where we're going to be taking roots of things with exponents. And the goal is to cancel out the exponent. And so you've got 2 categories. If your index is odd, it's an odd integer root. If your index is an even number, then it falls into the even integer root. So that number is either odd or even. So if it's an odd number, essentially, if whatever is underneath the root, the exponents cancel and you're just left with that number. So like if we have, let's see, the cubed root of -64, This is the cubed root. Here, actually, let's not write it as negative 64. Let's do negative 4 cubed. So the cubed root cancels out the exponent of 3, the cube, and that gives you an answer of negative 4. For even integers, we always take the absolute value because you can't get a negative answer with an even number for your root, because taking an even exponent only gives you positive values. So an example of this is if I had the fourth root of negative 2 to the fourth, the proper answer would be the absolute value of negative 2, which would be 2. Okay, question. What is the purpose of canceling out the exponent? So we want to cancel out, there's two situations. First is simplifying things that are inside of radicals. So being able to cancel out the exponent means that you're able to remove it from inside the radical to outside so you can actually work with it and do things. The second thing is we are going to be solving equations that have square roots, cube roots, and you want to cancel out figure a way to cancel these things out so that you can get stuff out of the radical and you can actually solve. So this is a very important thing to be able to solve these types of problems, which we will do next week, is when we're actually solving these. So this week we're practicing simplifying them, and then next week we'll use this to solve. So it's really important to get the basic rules down and how this works. So it'll make your life easier next week. So you have like a week to practice on this. So odd roots, you can get negatives out, and you can have negatives inside the radical. But if it's an even index, or that number is even, basically all of your numbers inside the radical need to be positive, or you have to take this absolute value sort of thing. So just as a general rule, that even roots can only have positives in there, except for when we throw in complex numbers, but that's something else that you'll see next week, I think. So that's how it works with numbers, is like you can even just put it on your calculator, take the cubed root. When you have variables, essentially what's happening is that our variable, the exponent on the variable, is getting divided by that index. So if you are taking the square root of x to the fourth, the square root is your index. So you're dividing that exponent on the inside by 2. And so to remove the exponent there, the x to the fourth, it now becomes x squared. And so if you have x to the sixth inside a square root, you divide that exponent by 2, and now it's an x cubed. If you have a cubed root, if that index is 3, you're dividing by 3. So if you have x to the sixth in a cube root, you divide 6 by 3 and you get x squared out. So the index matters because it tells you whether you're out, it makes a difference on your output. And so x to the ninth, you divide that exponent by 3, that gives you x cubed. And the reason why this works, let's take our square root of x to the fourth. That is basically x squared squared. So we've learned our rules of exponents. And if you have an exponent on top of another exponent, you multiply. So x squared squared would give you x to the fourth. So now I'm taking the square root of something that's squared. I'm left with what's underneath it, which is x squared. So let's have an example of the x to the sixth with the cubed root. So x to the sixth is the same thing as x squared cubed. So x squared cubed, you'd get x to the sixth. I'm kind of undoing that multiplication of exponents. And then the cubed root part cancels out the exponent, and this gives us x squared. So that's how this works. And the shortcut, so that you don't have to rewrite it, is just to divide that exponent by the index, the number that's outside. And if you have something that you can't divide, like if I had x to the 7th, 7 doesn't divide by 3, so I wouldn't be able to take the cubed root of x to the 7th unless I did some manipulation. And that's where we get into the product and quotient rules, because that allows us to do some manipulation of what we have so that we can cancel out the root and the exponent and get it outside of our radical. So we've got the product property and the quotient property. So the product property says that if you have two radicals multiply together and they have the same index, so they're both square roots or they're both cubed roots, you can make them one by multiplying what's underneath them. And you can also do the bottom, you can reverse it. So you can have things multiplied together inside a radical and split it up as multiple radicals multiplied together. The quotient property is basically the same thing, but with a fraction. So if you have things in a fraction and they have the same index, so they're both square roots, both cubed roots, whatever, you can combine them into a single fraction. Or if you have a single fraction inside a radical, you can split it up into two separate radicals. And so these two properties are used to simplify radicals, which is something we're going to learn this week. These products or these rules are not used for solving. That's more what I just showed, the being able to cancel out the radical. These are used basically just for simplifying. If you have to go on to like calculus, these are going to be important skills. So that's one of the things that, we have to teach a wide variety of skills for people going to various other math courses. So if you're somebody that you have to take calculus, like you're in engineering, you're going to want to make sure you have these and you have them written down because you will use them later on. And so we consider something simplified when you've got all of the exponents in the inside of the radical smaller than what's on the outside, the index on the outside. So like the cubed root of x to the 7th is not simplified because that 7 is larger than the outside, but the cubed root of x squared is simplified because it's smaller. So the cubed root of x to the 7th, we would have to do some manipulation to simplify that because it's not simplified. So we're going to be working to simplify things using these rules. And so these are the specific rules for how you know something that is simplified. Because I get a lot of questions from people, well, how do I know when to stop? So the radicand, so just to refresh, I'll just do different. This is called the radicand. What's up underneath the radical symbol? So it has no factor other than 1 that is a perfect nth power. So that means there is no exponent that is n because you can just cancel them out if it is. So the number on the inside, the exponents on the inside is just smaller than the outside. You don't want to have any fractions inside there. So if you have fractions inside the radical, you want to use the quotient property to split it up, and then you need to do some simplification. If we have fractions and radicals in the fraction, that's not allowed. So we have to do some work to get radicals out of the bottom of a fraction. And that exponent m can't be divisible by the outside, because if it is, then it needs to be simplified. So we're going to start with very simple ones. They're all c to the 7th. Sorry, I left my water downstairs. So I don't want any water to let this tickle out my throat. We're going to use the the product properties show you how to simplify these, because these, we can't just take the exponent and divide it by the number on the outside, because these don't divide. And we have c to the 7th. It can't be divided by 2 for the square root. It can't be divided by 3. It's not divisible by 4. It's not divisible by 9. So we're going to use the product property. So I'll start with the square root. So the goal of the square root is that you want to rewrite c to the 7th so that the exponent is an even number, because you can divide it by 2. Or we could just keep dividing it by 2, or splitting it into groups of 2. So I'm going to go the long way to show you how to do this problem, just so you can see what's really going on, and then we'll do like the shortcut way. So c to the 7th, that means we're multiplying c 7 times. So I'm going to start by just writing c 7 times multiplied together. And these are all inside the square root. So I gotta make sure that I usually do my square root last with things like this to make sure that it's covered over everything. So I've got 7 c's there because it's c to the 7th. Because it's a square root, you want to group them in groups of 2 because we're undoing squares. So we want to group them in pairs so that they have exponents of 2. So I'm going to group pairs of 2, and then I'm going to have 1 left over. So this is going to give me c squared times c squared times c squared, and then times c. So I'm doing this specifically because now I've got things that are exponents of 2. And now the product property says if you've got things that are multiplied inside a radical, you can split them up as multiple radicals. So this can be written as the square root of c squared times the square root of c squared times the square root of c squared times the square root of c. So that is the product property that allows you to do that. And now the square root cancels out the c squared, and you're left with just c underneath. So this will give us c times c times c. And then we have the square root of c that we can't cancel because that exponent 1 is smaller than the index, which is 2. So that's part simplified, but we could cancel out the exponents of 2 with our square root. And we end up with 3 c's multiplied together and then a square root of c. So this then gives us our final answer, which is c cubed times the square root of c. So this is the long way to do this problem. You rewrite your exponent c 7 times. You do the groupings matching the index. So if your index is 2, you want to group them in exponents of 2. Then you use your product property to split it up, simplify, and then recombine. So you can imagine that if you have an exponent of like c to the 100, you're not going to want to do it this way because you don't want to write c multiplied 100 times. So instead, as we do some smart thinking about how to divide up our exponents in such a way that we can divide it by that index. So I will demonstrate this with the cubed root of 3. So we have c to the 7th. Our index is 3. So we want to rewrite this so that we can take our exponent and divide it by 3 because that is the index on the outside. So instead of grouping, I could group these in groups of 3. So I could do a c cubed and then another c cubed. So that would give me 6 c's, and then a c to this, or a single c left over, to have a total of 7 c's together. So I can group them in groups of, 3, because that's our index. Or you just think and you're like, okay, 7 doesn't divide by 3, but you just keep counting down. You're like, but 6 divides this by 3. So what we can do is rewrite the inside as c to the 6 times c. So that c, you can write it as c to the 1 if you want. So that still adds up to 7, because our rules of exponents say when you're multiplying, you add the exponents. So that's still c to the 7. But now, and I forgot my cubed. I've got something with an exponent that I can divide by 3, the c to the 6. So I'm going to take my product property and split it up. And these are cubed roots, so I need to make sure that I remember to put that 3 there. So I'm splitting it up. So I've got the cubed root as c to the 6th, and then the cubed root is c. And then that cubed root of c to the 6th, I can simplify that. I can take that exponent of 6 divided by 3, which gives me 2. So that's going to give me c with an exponent of 2. And when I do that, it's no longer in the cubed root. And then I have this cubed root of c. And now that is simplified. The inside of the cubed root that I have left, the exponent is smaller than the index. And then I was able to take things from inside the radical, and now I have them outside the radical. So that's what we have as simplified. So let's do the same sort of thing with c to the 7th here. We've got c to the 7th and the 4th root. So that index of 4 means we want to have our exponent divisible by 4. So I have 7 does not divide by 4. 6 doesn't divide by 4. 5 doesn't divide by 4. So I can split it up as 4 and something with an exponent of 4 to divide it by 4. So I'm going to have c to the 4th, and then I need to make this c to the 7th. So I have 3 more in order to make it to c to the 7th. And then I've got the index of 4. So it's the 4th root. So now I'm going to use the product property and split this up. I've got the 4th root of c to the 4, and then the 4th root of c cubed. The 4th root of c to the 4, those cancel out. 4 divided by 4 is 1. So we'd have just an exponent of 1 when we remove it from the radical, which is just a regular c. And then I've got this 4th root of c cubed, and that 3 is smaller than the 4, so that does not simplify further. So for the cubed root, you want to have your exponent divisible by 3. For the 4th root, you want to have your exponent divisible by 4. So for each of these, how you split up your problem depends on what your index is, because that's going to tell you how you choose to split up your exponent and your multiplication. In this problem, parentheses are not required to indicate a multiplier. That is correct. So I don't need to put parentheses because they're next to each other and it's assumed that they are multiplication. In general, you only really need to put parentheses if you've got numbers that are multiplied together, so that it doesn't look like, if you had 2 times 3, it doesn't look like 23. Or if you've got addition or subtraction going on when you're doing multiplication. But we don't have any addition or subtraction, so we do not need any parentheses here at all. So you've just got your numbers here. Or, I mean, the alternative to using parentheses is to use the dot to indicate multiplication as well. So the last one here I have is the square or the 9th root of c to the 7. So we would need to have our exponent divisible by 9. The 7 is smaller than the 9, so there's no way that we're going to be able to split it up to be divisible by 9 because you're splitting it up and you're going to get smaller exponents. This is already simplified because that exponent on the inside is smaller than the index that's on the outside. So this one's already simplified and we can't do anything to it. So I've gone through 4 examples here, and that index, that number on the outside of the radical, really matters because it's telling you how you're splitting up your answer, and then it changes what your final answer looks like as well. So it's really important to pay attention to that. Are there any questions so far? I know you guys have had a few questions already, which is fantastic. Okay. So let's look at this with numbers. I started with variables because variables are the easiest type of radical to simplify, because all you have to do is split it up in a way that you can divide that exponent by the index. Those are the easiest ones. With numbers, we have to do prime factorization first. So you've got some extra steps that you have to do first before you can use these rules. And the rules are the same as when you have the exponent, where you can divide your exponent by the index. So the rules are essentially the same, but we have to write it in its prime factorization first before we can attempt to simplify. So I've got 2 different numbers here. We've got 24 and then 54, and both of them are going to be square roots and cubed roots. And those are the most common that you see. It's going to be square roots and cubed roots. So that's why I stuck with those. So first thing we want to do is the prime factorization for 24, which means starting with a factor tree. So I'm going to do it on the right so that I don't get it confused with the actual work here. So I need to split 24 up into 2 numbers that multiply to 24. And it doesn't matter what 2 numbers we split it up as. So I'll let you guys pick. You can put it in the chat, or you can say it out loud if you want to unmute yourself. But what are 2 numbers that when you multiply together, they get you 24? 3 and 8. That's good. That's not the first one I thought of. I thought of 6 times 4, but that's totally cool because it doesn't matter. 12 times 2 is another one we could have done. So you'll get the same answer either way. 3 times 8 was the first one that popped up, so we'll do that one. So 3 is a prime number, and then we've got 8. Well, 8, the only way to do it is 4 times 2. So I'm going to split 8 up as 4 times 2. 2 is a prime number, so I'm going to circle that. And then 4 can only be split up as 2 times 2. And those are prime. So once you finish and you've got circles, prime numbers at the bottom of your branches, we are going to rewrite this as a product of prime numbers. So 24, and we usually put the smallest number first. So it's 2 cubed, because there's 3 2's there, times a 3. So all of those, the prime numbers that I've circled, you would multiply together. So we've got 2 times 2 times 2 times 3, or 2 cubed times 3. So you have to do your prime factorization first. And now we're going to follow the same rules that we did when we had the exponents with the variables. I want my exponents to be divisible by 2 because this is a square root. So my 2 cubed, that 3 is bigger than the 2 that I want to group it in. So I can simplify that. And I can split it up as 2 squared times 2. So 2 squared times 2, and then times that 3. So I still have 3 2's there. I've just split it up differently so that I have something that has an exponent that I can divide by 2. Now the 2 times the 3, those I can't simplify further because those exponents are essentially 1, which is smaller than the exponent of 2 that I'm looking at for my index, the index of 2. So those cannot be simplified further. So we're going to split this up with the 2 squared part on itself and then the 2 times 3 by itself. And that will be how we're going to be using the product property. So we're going to have the square root of 2 squared, and then we're going to put the 2 times 3 together because those can't be simplified further. So we're going to put them in a single radical. So that's using our product rule. Then the next step is to simplify. So the square root of 2 squared, that square root cancels out the exponent of 2, and we're left with 2 on the outside. And then inside the radical, I recombine those to get the square root of 6. And so this gives us a final answer of 2 times the square root of 6. Now, Dylan asked earlier, why do we need to do this? So when we have actual numbers like this in the square root, this is how we simplify square roots when you have the quadratic formula. So the quadratic formula, you can put in your calculator and get fractions, or sometimes you get decimals often when you use it because it has a square root in the formula. And then you have to round your numbers. We don't like to do rounding unless it's a word problem. We like to have exact answers. And so when you're using the quadratic formula, you need to know how to simplify that square root and simplify like in a form like this, because often that will allow you to cancel out the fraction and then you don't have a fraction in your answer. So this particular skill, when you're working with only numbers, is really important with the quadratic formula to make the numbers smaller to work with. The variable stuff is more helpful with the calculus and then with the solving. So they've each got their little use here. Are there any questions on the square root of 24 that I just simplified? Okie dokie. So we'll do the cubed root of 24. So we already have the prime factorization done. So that's nice. I don't need to redo that. That's going to be 2 cubed times 3. Now, for the cubed root, you want to have exponents of 3. We've already got something that's an exponent of 3, so I can immediately split this up. So I'm going to use that product rule so that we have 2 cubed inside the cubed root, and then the 3 is going to be separate. So because that index is different, I'm splitting it up differently. So now the cubed root and the 2 cubed cancels, so I'm left with just the 2, just what's underneath there. And then I have this cubed root of 3 that I can't simplify because there's no exponent on the inside, so it's smaller than the outside, so that doesn't simplify any further. So the final answer for this one is 2 times the cubed root of 3. Having that cubed root allowed us to basically simplify an extra 2 out of there. So let's look at 54. We've got the square root of 54 and then the cubed root of 54. So we need to do our prime factorization of 54. So I'm just looking at the time and I think I might be running a little behind where I wanted to. So I will just do this one. So 54 is 9 times 6. So 9 can be split up as 3 times 3, which are prime numbers. And then 6 can be split up as 2 times 3. So 54, when I write it as the prime factorization, I've got a 2, and then I've got a 3, oops, I wrote 2 again, 3 to the third. And I'm looking at the square root here. So square root, I want to make them exponents that I can divide by 2. I can't divide 3 by 2, but I can divide 2 by 2. So I'm going to split that 3 cubed as 3 squared times 3. And I'm actually going to put that, I'm going to move that to the front because anything that I simplify, we put in front of our radical. So I'm going to just rearrange it. So I'm going to have my 3 squared times 3 and then my times 2. So I've moved that 3 cubed part to the front. And then I split it up as 3 squared times 3. And now that I have my things with my exponent out there, I'm going to split that up. So I have the square root of 3 squared, and then I'm going to have the square root of 3 times 2. So you can see that this is looking very similar to the square root of 24, totally different number, but what's underneath the radical on the right, the 3 times 2, is going to basically end up to be the same thing. So I've got my square root of 3 squared, so that cancels out and I'm left with 3. And then I can multiply the 3 times 2 and get 6. So this simplifies as 3 times the square root of 6. So the next one, we've got the cubed root of 54. So I'm going to rewrite it with 3 cubed first, just because I know that I'm going to be simplifying that cubed root of 3 cubed. So I've already got something with that exponent of 3. So I'm going to split my 3 cubed up. And then I'm going to leave the cubed root of 2 left over. Then that cubed root cancels out the 3 cubed and we're left with just the 3 underneath it. And then I have the cubed root of 2. So this is the procedure that you do for simplifying all of these things. And this is just using the product property. Are there any questions? Okie dokie. So let's look at the quotient property. And usually when you have the quotient property, you actually use both of them, use the product and the quotient properties to simplify. So when I have something that I have like a fraction inside my square root, cubed root, whatever, I like to simplify the fraction first, if possible, and then start dealing with the square root, cubed root stuff. So top left here, I've got the square root of y to the 5th over y. So our rules of exponents say that you can simplify that by taking the top exponent minus the bottom exponent. So that's what we learn with our rules of exponents, because that's a y to the first at the bottom, though that doesn't look like a very good one. So 5 minus 1 is 4. So this would be equal to y to the fourth. So now I have the square root of y to the fourth, and that square root means that I divide the exponent by 2. I can divide 4 by 2, so I don't need to rewrite this. I can just go straight to that. 4 divided by 2 is 2, so my answer is y squared. So I didn't even need to really use the product or quotient properties here, though we could have. It would have been more work. So I don't even try to use it if I don't need to, because I don't want to do more work than I have to. Next one, we have cubed root of 3 over the cubed root of 24. So in this situation, I have two separate radicals. If there's two separate radicals, I like to combine them into a single radical first so I can simplify my fractions, and then expand them out and go from there. So I would be using the quotient rule, which allows me to recombine these into a single fraction. So now I have 3 over 24, and I can reduce that fraction by dividing the top and the bottom by 3. So this gives me the cubed root of 1 over 8. So now that I've simplified that radical, now I use the quotient rule again to split it up. This is how I work it. You may find that this doesn't work for you, but this is what works for me. So then after I simplify, I split it back up. So that way I have now the cubed root of 3 over the cubed root of 8. So the cubed root of 1 is 1. The root of 1, it doesn't matter what the index is, it's always going to give you 1. So whether it's a 4th root, 5th root, whatever, that's always going to give you 1. So that's going to be 1 on top. 8, this is 2 cubed. You want to kind of memorize that because that's going to pop up a lot. So I'm going to rewrite this as 2 cubed, but you want to basically memorize that the cubed root of 8 is 2, so you can go straight to the answer and you don't have to write the step where you write it with the exponent. But 8 is 2 cubed, so I can rewrite that as 2 cubed. And then you see I can take the cubed root of 2 cubed and those cancel out, and I'm left with an answer of 1/2. So that's how I do this problem. A problem like this is that I will recombine them, simplify, split them up, and then reduce them and use my rules with the radicals. Next, I have another square root. We've got q to the 11 over q to the 5th. So again, when I see something like this, and I know that I can simplify I can do the 11 minus 5 to simplify that. I will subtract those. So that gives me q to the 6th inside the square root. And then I can, again, it's a square root. I divide the exponent by 2. 6 divided by 2 is 3. So this will give me q cubed left over. So that's the way that I do it, just like I did the first one. Now, the alternative way, if you don't like that method, and I prefer that method, is to split it up by using the quotient rule first. splitting it up as two separate square roots. Then you would, inside these, split up your q's. So like if I have q to the 11 and I have a square root, I want to make it divisible by 2. So if I go down 1, that's 10. 10 can divide it by 2. So I can split this up as q to the 10, and then I have an extra q to make it 11. And the same thing in the bottom. If I have q to the 5th, I can make it q to the 4th, and then extra q to get 5 of them there. So then we can use our product rule to split up these fractions or these radicals. So I can split up the q to the 10 into its own from the q, and same thing with q to the 4th and the q. And when you do it this way, in this case, our square roots of q can cancel out because those are the same on the top and the bottom. And then I take the square root of q to the 10th. 10 divided by 2 is 5, so I get q to the 5. And 4 divided by 2 is 2, so I get q squared. And then you can subtract the exponents, 5 minus 2, and get you q3, which is the same answer, but a lot more work. So that's why I use the method that I used before, where I simplify first and then I deal with the radical, because it's a lot less work. So the cubed root of 2 over the cubed root of 250. So this is similar to the one that I had with 3 and 24 there. And I combined those first, then did the radical. I'm going to do it the other way, where we do the radical stuff first, then so I'll do it the opposite way so you can see how that would work, and then you can kind of pick which method you want. But first, so 250, I need to do a prime factorization. So that's 25 times 10. 25 is 5 times 5. And then 10 is 2 times 5. So if I'm going to do this, what I call the long way, I actually don't know if it's longer. So I need to split up the cubed root of 250. I've got 3 5s, so I'm going to put that first. 5 cubes times 2. So that's one way to do this. And then in the denominator there, I can split up that multiplication into 2 separate cubed roots. So I have the cubed root of 2 over the cubed root of 5 cubed times the cubed root of 2. And just like the other one that I did just above here, our cubed root things, they cancel out here. And so we're left with a 1 on top. If everything cancels out, you're left with a 1. And then in the denominator, we have the cubed root of 5 cubed, which that cancels out and you're left with 1 over 5. So it's about the same amount of work as what I did with the cubed root of 3 over the cubed root of 24. It looks like about the same amount of steps. I did need to do the prime factorization versus reducing it first. But you get this, you would get the same answer whether you combine them first, reduce, and then split it up, or if you don't try to combine them all and you just use like the product rule to try to simplify. So are there any questions? Okay, so I definitely have more examples than I have time to go over. But I will do as many I have in the next 10 minutes. So we're going to start throwing in these numbers together with variables. so that you're working multiple of these things at the same time. So I'll start with, I've got the square root of 25ab cubed. So 25 is 5 times 5. So I'm going to just start by rewriting that as 5 squared. And then I'm going to put my b cubed first and then the a, because I'm just putting things with the exponents in front because I know those are the things that I want to try to simplify. So it's a square root. I need my exponents to be divisible by 2. So 5 squared, we're good. We can divide that by 2. The b cubed, we can't. So I need to split that up as a b squared and then a b. So I still have 3 of them, but I've just got something I can divide by 2. So I'm going to have 5 squared, then a b squared, then a b, and then an a. So I've split up this b cubed as b squared times b. So you're working multiple things when you have numbers and variables, and you're still trying to get your exponents that are divisible by whatever's outside. So now that I've got my 5 squared, my b squared, I'm going to group those together, and then I'm going to group the b and the a together. So I'm going to use the product rule, and I'm going to have 5 squared, b squared in one grouping, and then the b and the a in the other grouping. I'm going to just rewrite those as ab. Actually, I don't want to confuse you guys too much. I'll write it as b, a, and then maybe I'll flip them in the next step. So I split the things that I can divide my exponents by 2 and the things I can't. So I could split those exponents by 2 more. I can make it square root of 5 squared, square root of b squared. I normally don't, and I skip this step, but you can do that. And then we've got AB. And then that square root of the squares, those cancel. So you're left with 5, and then you have a b, and then you have your square root of AB. And these are all multiplied. So we usually write it as 5b and then the square root of AB. So you're putting them together. Write my 5 there. So I usually skip this step right here because I know when I take the square root, the exponent divides by 2. So I usually skip that and go straight to the 5b and just divide each of those exponents by 2. And then I have them in front. But all I'm doing is just skipping a step there that we're doing. You know, I just, you know, these things take a long time writing. So I want to show you every single step, but you want to, I mean, you're probably not going to get to this point in this class, but the goal is to get to a point where you can do a lot of this in your head and you don't need to show all of these steps, but you're not going to be there right away. So that's how I simplify this one. Let me, so we've got 6 minutes. I'm going to skip to my next slide because I want to do a different one here because I don't have a lot of time. So let's do the one on the left, cube root, the negative 192, a to the 6th, b, c squared. So a negative is okay when you have an odd exponent. So the 3 is odd, so that's okay to have a negative there. And that's going to tell us we're going to have a negative on the outside. Just so, just remember that if you have a negative inside a radical with an odd index, your answer will be negative. So I'm going to take my 192 and I need to make a factor tree. So I know it's divisible by 2 because it's even. So I'm going to take my calculator. 192 divided by 2. Okay, that's 96. I know I can divide that by 2 because that's even. Gives me 48. Okay, I know 48 is 6 times 8. That's 2 times 3. So factor trees can get pretty long if you don't choose bigger numbers to divide it, but that's my factor tree. So I'm just kind of rushing here because I know I'm nearing the end of, it's almost been an hour. So 192, I've got my cubed root here and my negative. So I've got 1, 2, 3, 4, 5, 6 2s. So it's going to be 2 to the 6 times 3. Now I've got a to the 6, and I want my exponents to be divisible by 3 because it's a cubed root. So that's okay. So I don't have to split a to the 6th at all because I can divide that by 3. So now I'm going to take all the exponents I can divide by 3 and move them in front, and then everything that I can't divide by 3 to the back, basically. And I'm going to keep that negative. And then I've got my 3bc squared. And then I'm going to split this into 2 or multiple radicals. So I won't skip that step. I'll take the cubed root of negative 2 to the 6th, cubed root of a to the 6th, and then the cubed root of 3bc squared. And the c squared, that 2 was smaller than the 3, so we can't take that radical. So the cubed root of negative 2 to the 6th, that negative, if it's a cubed root, that just goes in front. And then I deal with the 2 to the 6. So the 6 divided by 2 is 6 divided by 3 is 2. So my exponent on the 2 is going to be a 2. So I'm going to get a negative 2 squared. Then for the a, I have cubed root of a to the 6. 6 divided by 3 is 2. So I get a squared. And then I have my cubed root of 3bc squared. So now I'm going to actually square that too. 2 squared is 4. So I'm going to get a negative 4a squared. And then I have the cubed root of 3bc squared. And that is our simplified answer there. So when you've got multiple things going on, usually when you're simplifying these, you got to rearrange things so that they're in an easy spot for you. So I rearrange my numbers and I put the things that I know that I can simplify first, and then I put the rest of it in the back. And then okay, I've got a question. How did the 3 change from 3a to 3bc? So that was rearranging. Let me color code here. So we have this 3, that's now over here. I've got this a to the 6th, that is just over there. So all I did was flip-flop where these were located. Maybe I shouldn't have chosen orange. Looks too close. There we go. So all I did was rearrange the order, because you're allowed to rearrange the order of multiplication. So the 3 was in front of the a to the 6th. I just flip-flopped it so the a to the 6th was first. And then that allowed me to put the things with my exponents that I could divide by 3 at the front. And then that attached the 3 to the b times c, because all of these things are multiplied together. So multiplication, commutative property allows us to rearrange the order of things that are multiplied. So you can just rearrange anywhere where they are in this any way you want. But you want to try to do it in a smart way that makes it easier for you. So if color coding helps you keep track of everything, go for it. Like I can, like color code each of these so you can see where they're located and where they're ending up. Let's do this one in the orange. And see, I think we can do this one red. So they're all still there. They're just being rearranged in different places, essentially. So I can even make my negative. Yeah, color coded. Yeah. So if you need to color code when you're doing this on paper, go right ahead. I mean, there's a reason I have highlighters all over my. Sometimes it helps you see where things moved around and where they are. So we're just literally just moving things around to simplify them. Other questions on this problem? I definitely don't have enough time to go through more. We've already hit our hour, but are there other questions? Okay. Well, so hopefully this is you were able to follow this. This is probably one of the harder things this week is doing these simplifying radicals. So not tomorrow, Friday's New Year's Eve, and then Christmas is, Saturday, and I'm going out of town. I know a lot of you guys are going out of town. I'm going to do my best to get all of my grading done by the end of the day tomorrow. Normally grading has to be done by Friday at the end of the day, but Friday I'm going to be driving 8 hours. So I'm going to try to get it done early, but if everything is not graded by Friday, I will finish it probably Sunday because, I want to actually take Christmas off. So I may be a little late on grading this week because of the holiday, just an FYI, because I'm, trying to get everything in. And also I know that you guys may be late on your stuff because of the holiday. So I'm not going to take any late penalties off of anything that you like homework or the quizzes that you do in Alex. I do want to make sure that you do the discussions on time in the week. So those will still have like a late penalty applied if you're late on the discussion. But the rest of the stuff, I know with the holiday, things get crazy. So if you're a little late, don't worry about it. I'm probably going to be a little late in my grading. I'm going to try not to, but I know it's hard with a lot of traveling and all that. So I just wanted to give you guys a heads up there. And then because, that was why we adjusted this live to be Wednesday, because I know that it's going to be a crazy weekend, but the next live for week 4 will be at the normal time, 7 o'clock on Sunday, because I will be back from my family trip. I'm driving back on New Year's Day. So I will be back in town and we can do our live for week 4, and that will be at our normal time. So just want to give you guys a heads up about that. So happy holidays. Thank you for coming. And I will see you guys at the next live. I'll be, of course, working next week. I did take a vacation day on Tuesday. So just as an FYI, but I'll be working and available and all that kind of stuff. So I will see you guys later, and I hope you guys have a wonderful holiday. So take care. Thank you for coming today.